The final frontier is about to become a construction site. A materials revolution is quietly unfolding, and it promises to make building in space practically limitless. By the end of this, you will understand exactly how we are overcoming the ancient barriers of cost and durability to create a permanent presence beyond Earth. We are moving from hauling every single beam and bolt from our planet to fabricating entire habitats from moon dust and engineering materials that repair themselves. How can a spaceship seal its own punctures? And what does a metal stronger than diamond have to do with building cities in orbit? What does it truly mean for our species to finally have an unlimited building lot among the stars? Think about the sheer weight of that limitation. Every single beam, every bolt, every panel for a structure in orbit had to be forged on Earth, then carried on an incredibly expensive and dangerous journey upwards. It was like deciding to build a house on a remote mountain peak, but insisting on manufacturing every single nail and plank in a factory at sea level, and then hiring a helicopter to fly each piece up individually. The cost was astronomical in every sense of the word. This reliance on terrestrial materials meant our ambitions were constantly being dragged back down by gravity and budget. We were trying to build a new world in space using a toolkit designed for the old one, and the tools were failing. Metals that are strong and reliable on Earth can turn brittle and shatter in the deep cold of space. Their surfaces can be slowly sandblasted into weakness by microscopic debris, or their internal structures altered by relentless cosmic radiation. The very sunlight that gives us life becomes a searing, unforgiving torch that can warp and degrade materials never designed for such exposure. This was the fundamental paradox we faced. We had the vision to reach for the stars, but we were building with materials that simply could not survive the journey. Breaking free from this paradox required a complete rethinking of what a building material even is. This ultimate recycling begins with the very ground beneath an astronaut's boots. In-Situ resource utilization, or ISRU, is the technical term for a beautifully simple idea: building with what you find instead of hauling everything with you. Picture a future lunar base. Instead of arriving as a prefabricated kit from Earth, it grows from the moon itself. The gray, dusty soil, known as regolith, is not just dirt, it is a construction material waiting to be unlocked. Enormous lenses or mirrors concentrate the raw, unfiltered sunlight of the lunar day, focusing that energy to melt the regolith layer by layer. This process effectively 3D prints solid, ceramic-like structures directly from the lunar surface. The same soil can also be baked in ovens to release oxygen, a vital resource for both life support and rocket fuel. In one sweeping move, the barren landscape transforms into a quarry, a factory, and a power source. This is how a landing pad gets built, not with concrete delivered from another world, but by sintering the dust already there. This is how a habitat gains a thick, protective shell against cosmic radiation, by piling that same local soil around its walls. ISRU reframes the entire challenge of space settlement. The problem of scarcity vanishes, replaced by the opportunity of infinite local materials. It is the foundational principle that makes every other advancement possible, turning the dream of a self-sufficient outpost from a fantasy into a matter of engineering. But this revolution does not stop with reshaping local dirt. We are moving from using what we find to engineering what we need, atom by atom. This is the domain of metamaterials, substances whose power comes not from their chemical makeup, but from their meticulously designed internal architecture. Think of it as building a material like you would build a cathedral, with a specific, intricate structure that gives it incredible strength despite being mostly open space. By controlling the shape and arrangement of these tiny, repeating units, scientists can create properties that defy nature. one of the most astonishing possibilities is a form of invisibility. By designing a metamaterial with a negative refractive index, we can theoretically bend electromagnetic waves like light or radar around an object. For a satellite, this could mean a perfect cloak, making it undetectable to sensors and safe from targeting. The same principle could be used to shield astronauts from harmful cosmic radiation, steering these invisible particles safely around a habitat. The strength of these engineered materials is equally mind-bending. We can create ultralight lattices, metallic frameworks that are 99% air, yet possess a strength-to-weight ratio that dwarfs solid diamond. Imagine the framework for a colossal space station, a solar power collector the size of a city, built from a material that is both incredibly strong and almost light as a feather. This eliminates the crushing mass penalty that has always grounded our grandest orbital designs, and these materials are not static, they can be programmed. A support beam in a lunar outpost could sense an incoming meteoroid shower and instantly stiffen its structure to absorb the impact. A solar panel could change its shape to optimally face the sun without any moving parts. This is a fundamental leap from discovery to design. We are no longer just searching for useful rocks or metals. We are creating entirely new rules of physics for our materials to obey. This mastery over matter itself points toward a future where our structures are not just passive shelters, but active, intelligent partners in our survival. This vision of intelligent architecture leads us to materials that do not just endure, but actively fight back against decay. We are now engineering the first generation of living building blocks, smart polymers that can feel injury and heal themselves. The principle is as elegant as it is revolutionary. Within the polymer matrix, countless microscopic capsules are suspended, each one a tiny vial of liquid healing agent. When a crack forms, it rips through these capsules, releasing the agent into the breach. This substance then undergoes a chemical reaction, often triggered by the surrounding material, effectively creating a new polymer that binds the crack shut. It is a process eerily similar to how a small cut on your finger clots and seals itself, a built-in emergency response system at a molecular level. For a spacecraft hull, this could mean the difference between a tiny, self-sealing puncture and a catastrophic decompression, all without a single astronaut lifting a tool. But some systems are designed for even greater resilience, mimicking the circulatory networks found in nature. These advanced polymers contain a vast, intricate network of tiny, hollow channels, much like synthetic blood vessels. When damage occurs, healing fluids are pumped from reservoirs through these vascular networks to the exact site of the injury, filling the crack and hardening. The true marvel is that these networks can be refilled, allowing the same structure to heal itself repeatedly over many years. A critical support beam in a Mars habitat, subjected to the constant stress of temperature swings, could maintain its integrity across decades, healing its own microfractures long before they could become a serious threat. The concept of a million-mile warranty takes on a whole new meaning when the product is capable of its own repairs. These polymers are not just healers, they are also sentinels. By embedding them with networks of microscopic sensors, we can give the material itself a nervous system. These sensors constantly monitor for strain, sudden impacts, and extreme temperature fluctuations. The structure gains the ability to report its own health in real time, sending data on developing stresses long before any visible damage appears. This transforms maintenance from a reactive scramble following a failure into a calm, proactive management of the structure's well-being. Can you envision a space station that sends an alert, not because a component has broken, but because it anticipates a future weakness and has already begun the healing process? This shift is fundamental. We are moving from building inert objects to cultivating dynamic, responsive systems. Our future in space will not be built with static steel and concrete, but with these resilient, almost biological partners, designed not merely to exist in the void, but to truly thrive there for generations. Yet the ultimate strength for our cosmic structures may come from the most fundamental of elements, carbon, reimagined on an atomic scale. Carbon nanotubes and graphene represent a leap into a new class of materials, where the arrangement of atoms matters more than the substance itself. Imagine a chain where every link is a perfect, hollow cylinder composed of a single, unbroken sheet of carbon atoms woven into a hexagon pattern. This is a carbon nanotube. Individually, these tubes possess a strength hundreds of times greater than that of high-grade steel, yet they are so lightweight it defies intuition. This combination of immense strength and minimal mass makes them the only conceivable candidate for a project as audacious as the space elevator. A cable woven from these nanotubes could theoretically stretch from Earth's surface into geostationary orbit, creating a permanent highway to space that would replace rockets for most cargo, slashing the cost of reaching orbit to a fraction of what it is today. But the wonder does not stop with tubes. Flatten that same atomic sheet into a single, two-dimensional layer, and you have graphene. This material is not only phenomenally strong, it is also a superstar conductor, effortlessly moving both heat and electricity. It is nearly perfectly transparent, yet so impermeable that not even a single helium atom can pass through it. These properties converge in spectacular applications. A solar sail made of ultra-thin graphene could capture the faint pressure of sunlight itself for propulsion, while also serving as the spacecraft's primary power grid and a shield against harmful radiation. The true breakthrough, however, lies in combining these forms. We are no longer talking about using carbon as a simple component, but as the very blueprint for an entire vehicle. Researchers are pioneering methods to manufacture these carbon allotropes in the pristine environment of microgravity. Free from the distorting forces of Earth's gravity, we can grow these atomic structures with a perfection and on a scale impossible to achieve on our planet. This opens the door to fabricating entire spacecraft frameworks that are born in the void, structures where the hull is also the power conduit, the radiator, and the primary shield. This is the promise of carbon, a future where our strongest and most versatile buildings in space are woven from little more than air and starlight. Strength is only one part of the equation for surviving in space. The real test is endurance against temperature swings so violent they could turn steel brittle as glass. On the Moon, a single day can swing from the boiling point of water to hundreds of degrees below freezing. During atmospheric entry, a spacecraft's skin must endure a firestorm hotter than the surface of the Sun. This is the domain of advanced ceramics and their remarkable hybrids, Cermets. These are not the delicate pottery of Earth, but materials engineered from the atomic level up to laugh in the face of such extremes. Ultra-high-temperature ceramics represent one pinnacle of this effort. They are so resilient they can maintain their shape and strength at temperatures exceeding 3,000 degrees Celsius. This makes them the only choice for the most punishing components, like the throat of a rocket nozzle where superheated plasma erupts, or the leading edge of a spaceplane slicing through the atmosphere at many times the speed of sound. They are the ultimate heat shield, a material that does not simply absorb punishment, but remains structurally intact while glowing white-hot. Yet pure ceramics can be brittle. The true genius lies in a fusion, creating Cermets. These composite materials marry the incredible hardness and heat resistance of a ceramic with the toughness and slight flexibility of a metal. Imagine a gear or a bearing for a rover on Mars. The red planet's fine, abrasive dust would grind standard metal parts into uselessness in short order. But a component made from a Cermet would resist that wear spectacularly, its ceramic side shrugging off abrasion while its metallic matrix prevents catastrophic cracking. This same resilience extends to the very fabric of space itself. In low Earth orbit, A thin haze of atomic oxygen slowly but relentlessly chews away at many materials, a corrosive sandblasting on a microscopic scale. Ceramics and cermets are largely immune to this decay. Their resistance to radiation is another superpower, making them ideal for building shelters and boxes to protect the sensitive electronic brains of our spacecraft and habitats on long journeys through the radiation-soaked void. By mastering these materials, we are not just building things that can survive a brief visit to a harsh world. We are creating the foundational parts for machinery that will operate for decades on the dusty plains of Mars, within the frigid craters of the Moon, and in the searing proximity of the Sun. This is how we build not for a mission, but for a millennium. The final leap in this materials revolution asks us to look not forward, but around us, to the biological masterpieces that have been evolving for eons. Nature holds blueprints for structures that are simultaneously resilient, lightweight, and produced with breathtaking efficiency. This is the realm of biomimicry, where we are learning to build by borrowing from life's oldest and most tested designs. Consider synthetic spider silk. On Earth, this material is already known to be stronger than steel by weight and tougher than the Kevlar used in bulletproof vests. But in the gentle embrace of microgravity, its potential transforms. Without gravity's constant pull, we could spin this protein fiber into vast, incredibly delicate orbital webs. These could act as passive capture systems for space debris, or as the ultralight structural frames for massive solar arrays that would collapse under their own weight if built on Earth. This is not science fiction, it is applied biology, using nature's recipes to solve problems in an alien environment. We can go beyond mere imitation and actually partner with living organisms to construct our future homes. Mycelium, the intricate root network of fungi, behaves like a self-assembling construction crew. By introducing fungal spores to a mixture of nutrients and local materials like Martian regolith, we can guide this living matrix to grow into predetermined shapes, from bricks to entire architectural forms. Over time, the mycelium consumes the nutrients and weaves through the soil, creating a solid, composite material that is both strong and insulated. Imagine a habitat on Mars that is not landed but cultivated, its walls literally grown from the red dust itself. This process requires very little energy, turning a barren landscape into a living workshop. The biological partnership deepens even further with engineered bacteria. Scientists are working with microbes that can be programmed to excrete calcium carbonate, the primary component of limestone and cement. Deployed in a crack on a concrete foundation, these tiny organisms would fill the gap with their own waste, effectively creating a biological sealant that hardens in place. On a larger scale, we could direct these microscopic builders to deposit layer upon layer of this biological cement, slowly building up a wall or sealing a pressurized habitat from the inside out. The line between a construction site and a cultivated ecosystem begins to blur. How do we define a building when its walls are alive, when its structure is a collaborative effort between human design and biological process? This fusion of biology and engineering points toward a future that is not just sustainable, but truly organic. Our expansion into the cosmos may not be a story of conquering harsh worlds with brute force, but one of learning to work with them, of cultivating our presence as much as constructing it. The final frontier could become a garden where our strongest materials are spun by silkworms and our safest shelters are grown from fungus. It suggests a profound shift from seeing the universe as a place to build, to understanding it as a place where we can finally learn to grow. The very gears that turn the machinery of space industry demand a perfection that ordinary metals cannot provide. They must spin for decades, perhaps centuries, without a single drop of oil or the touch of a maintenance tool, in an environment that actively seeks to grind them into dust. This is where a new class of material emerges from the furnace, one that defies the very definition of metal, bulk metallic glasses are forged from a paradox. We are taught that metals are crystalline, their atoms stacked in neat, repeating rows like soldiers on a parade ground. But these rows create planes of weakness, tiny faults where cracks can begin their slow, inevitable propagation. Bulk metallic glasses shatter this crystalline prison. By cooling a molten metal alloy with incredible speed, its atoms are frozen in place before they can form an orderly lattice. The result is a solid with the chaotic, disordered structure of window glass, but possessing the strength and versatility of a high-performance alloy. This atomic chaos is its greatest strength. Without grain boundaries to serve as highways for failure, these materials become incredibly hard and resilient. They can be bent and spring back to their original shape with a remarkable elasticity that would permanently deform a conventional metal. Their surfaces are naturally smooth, almost frictionless, making them the ultimate candidate for the bearings and gears inside a construction robot on the moon or the precision actuators of a satellite that must function flawlessly for generations. Imagine a gearbox assembled on Mars, its components formed from bulk metallic glass. The fine, abrasive dust that would quickly wear down steel parts is met with a surface so hard and uniform it simply resists the attrition. The true engineering marvel, however, lies in how these materials are shaped. When heated, bulk metallic glasses become soft and pliable like plastic. This allows them to be thermoplastically formed into incredibly complex, net-shaped components in a single, elegant manufacturing step. In the constrained environment of a space station or a lunar factory, this is a game changer. Instead of launching a box of separate gears, shafts, and housings that then require precise assembly, you could produce a complete, intricate mechanism as one seamless piece. This eliminates assembly errors, reduces mass, and creates a device with inherently fewer points of potential failure. Their resistance to corrosion is another silent superpower. In low Earth orbit, a thin haze of highly reactive atomic oxygen slowly eats away at many materials, a silent, invisible decay. Bulk metallic glasses stand firm against this assault, their non-crystalline structure offering no easy entry points for chemical attack. This combination of properties makes them the unsung heroes of the in-situ factory, the durable, self-lubricating, and maintenance-free components that will keep the entire system of space construction running smoothly long after the engineers who built them are gone. They are the perfect, disordered foundation for the most reliable machines we have ever built. But these resilient, almost biological structures still need eyes. For a habitat floating in the void or a greenhouse on a distant moon, a window is not a luxury. It is a psychological necessity, a fragile looking glass that must also be an impregnable shield. This paradox finds its answer in a material that seems to defy its own nature, a ceramic you can see right through. Aluminum oxynitride, often called transparent aluminum, is one of the most astonishing creations of modern materials science. It looks like a thick piece of high-quality glass, but its true character is revealed under assault. Where silica glass would shatter into 1,000 pieces, this transparent ceramic can stop an armor-piercing bullet in its tracks. That same incredible strength and hardness makes it the ultimate candidate for a viewport on a deep space vessel. The constant, invisible rain of micrometeoroids and space debris, which would pit and cloud standard glass over time, barely leaves a mark. It is a material that offers a crystal-clear view of the cosmos while possessing the durability of a battleship's armor. Its resilience extends to the environmental extremes of space itself. Unlike many plastics or composites that can turn yellow and brittle under the relentless barrage of cosmic and solar radiation, aluminum oxynitride remains optically perfect. It can withstand searing heat and profound cold without warping or losing its clarity. This makes it ideal not just for the windows of a crew capsule, but for the vast observatory domes planned for the far side of the Moon, where telescopes will peer into the depths of the universe through an atmosphere-free dome. Those domes will need protection, and this transparent ceramic provides it without obscuring the view. The same principle applies to the protective covers for sensitive solar arrays, where any clouding or damage would mean a direct loss of power for the entire station. The development of such materials is about more than just engineering safety. It is about designing for the human spirit. Long-term space habitation carries the risk of profound isolation. The ability to look outside, to see the Earth as a blue marble, to watch the stars drift by, or to tend plants in a sunlit greenhouse, provides a cognitive and emotional anchor that is impossible to overstate. With a clear, strong barrier, we can bring the outside in. We can maintain that vital, life-affirming connection to the universe we are exploring, all while remaining perfectly safe within a shell that is as clear as air and as strong as stone. It is the final piece in creating a home, and not just a habitat among the stars. Radiation does not announce its presence with a sound or a flash. It is a silent, invisible rain that falls through everything, including our own bodies. For a crew on a multi-year mission to Mars, this is not a secondary concern. It is one of the most formidable barriers to human exploration. The conventional solution is mass, thick slabs of metal or water to absorb the harmful particles, but mass is the one thing we cannot afford to launch in great quantities. This is where the magic of aerogels enters the story. To hold a piece of aerogel is a strange experience. It looks like a ghost of a solid, a frozen blue smoke. It is the lightest solid material ever created, composed of up to 99.8% air. Its structure is a labyrinth of microscopic pores, a nanoscale sponge. This architecture makes it a phenomenal insulator, capable of protecting a habitat from the 500-degree temperature swing between sunlight and shadow. But its true genius for space travel lies in its emptiness. By impregnating this porous network with hydrogen-rich compounds, we create a shield that is both incredibly light and astonishingly effective at disrupting the high-energy particles of cosmic radiation. Hydrogen atoms, being the smallest and simplest, are perfect for scattering incoming radiation, and the vast, tangled pathways within the aerogel give those particles an immense journey before they can possibly penetrate through. It is like trying to run through a forest where the trees are impossibly dense and close together. The runner quickly loses all their energy. This means a layer of aerogel can provide the protective power of a much thicker, heavier slab of aluminum, but at a fraction of the mass penalty. The same principle of using structured emptiness applies to metals. Foamed metals are what you would get if you could solidify the froth on a cappuccino into a durable, metallic sponge. They are solid metal, typically aluminum, but shot through with a uniform network of gas-filled pores. This structure gives them a remarkable set of properties: high stiffness and strength combined with a very low density. They are also exceptional at absorbing energy, making them perfect for impact protection. Imagine the landing legs of a lunar lander crafted from foamed aluminum. As the craft touches down, the foam compresses in a controlled, predictable way, dissipating the force of the landing and protecting the delicate cargo inside. Or picture a micrometeoroid shield for a space station, a layer of this metallic foam that can absorb the incredible energy of a high-speed impact by collapsing its pores, trapping the debris and preventing it from reaching the pressurized hull. These materials represent a fundamental shift in our approach to protection. We are no longer relying on brute thickness and weight, but on intelligent, intricate internal designs borrowed from nature itself. With aerogels and foamed metals, we can wrap our explorers and their homes in a veil of safety that is almost as light as the void it defies. This vision of intelligent, self-healing structures is now evolving into something even more dynamic, a material with a built-in blueprint for transformation. We are entering the era of programmable matter, where the very substance of our construction can be commanded to change its form, its properties, or its function over time. This is the core of what some call 4D printing, where the fourth dimension is not space but time itself. Think of it not as creating a static object, but as printing a latent potential for change directly into the material's molecular code. The most immediate application lies in solving the ancient problem of space logistics. Picture a single, dense block of material packed efficiently inside a rocket's payload fairing. It looks like little more than a solid brick, but once it reaches the vacuum of orbit and feels the gentle warmth of the sun, a silent, pre-programmed ballet begins. The block unfurls, its internal structure shifting and expanding, locking into place as a vast, intricate truss designed to support a massive solar array. This self-assembly is not magic, it is engineering at its most elegant. It is achieved by printing with smart materials like shape memory polymers or alloys. These substances have a kind of molecular memory. They are manufactured and programmed in one shape, then temporarily folded and compressed into a compact, stable form for launch. The trigger for their transformation is something simple and abundant in the space environment: a specific temperature, a certain wavelength of light, or even a magnetic field. Upon sensing this cue, the material remembers its original, intended form and gracefully returns to it, all without a single command from Earth or a risky spacewalk. This fundamentally rewrites the rules of deployment. It means we can design structures that are far larger than any rocket fairing, knowing they will blossom into their final, functional shape only when they reach their destination. The need for complex and dangerous astronaut-led assembly missions in the harsh void is dramatically reduced, but the potential goes far beyond a one-time unfolding. This technology points toward a future of truly dynamic space architecture. A communication satellite's antenna could reshape itself to optimize its signal for different regions of Earth. A scientific instrument could extend or retract its booms to avoid debris or to fine-tune its measurements. We are no longer just building in space. We are cultivating structures that can adapt, respond, and evolve to meet the changing demands of their mission. This is the ultimate expression of efficiency and resilience for an environment where every gram and every maneuver counts, a future where our strongest materials are also our most intelligent shapeshifters. Even the most resilient materials need an invisible suit of armor. Beyond the bulk shielding that forms a habitat's walls, a more subtle battle is waged on the very surface of every structure and suit, a daily defense against the silent rain of solar and cosmic radiation. This is where advanced coatings come into play, acting as a critical first line of defense. Scientists are engineering multi-layered nanocomposite films, some designed to act like microscopic mirrors that reflect high-energy particles away, while others are formulated to absorb that violent energy and dissipate it as harmless, radiated heat. Imagine a future spacesuit for a Mars walk. Its outer layer not just fabric, but a sophisticated coating that actively turns deadly radiation into a faint warmth, a passive and continuous protection for the person inside. The ingenuity deepens with designs that trap thin layers of water or hydrogen-rich polymers between durable ceramic shells. Since hydrogen nuclei are perfect for scattering incoming radiation, this creates an incredibly lightweight, yet highly effective barrier. The development of these smart skins is not a luxury. It is a fundamental requirement for the hardware of deep space. Sensitive electronics can be fatally disrupted by a single energetic particle, and the long-term integrity of human DNA must be preserved over years, not just months. By perfecting these reflective and absorptive surfaces, we are giving our explorers and their machines a fighting chance against an invisible environment that never stops its assault. This is how we build for longevity, ensuring that a mission's success is not undermined by the slow, cumulative decay that space inflicts on all things. But the ultimate factory for these new materials may not be on any world at all. It is the environment of space itself. Microgravity offers a purity of condition that our planet simply cannot provide, removing the dominant force that has shaped every industrial process in human history. Without gravity's constant pull, materials behave in fundamentally new ways. On Earth, if you try to mix two molten metals with very different densities, the heavier one will inevitably sink, creating an imperfect, layered alloy. In the quiet of orbit, that separation never happens. The metals remain suspended in a perfectly homogeneous mixture, allowing us to create novel alloys with combinations of strength, lightness, and thermal properties that are literally impossible to forge on the ground. This same principle of perfect suspension revolutionizes other fields. The growth of protein crystals for pharmaceutical research is a prime example. On Earth, these delicate structures become misshapen and flawed as they form, distorted by gravity-induced convection currents in their solution. In microgravity, they grow large, perfectly ordered, and exquisitely structured. This crystalline perfection provides drug researchers with a far clearer blueprint of a protein's shape, dramatically accelerating the development of new medications for challenging illnesses back on Earth. The profound silence of the vacuum is another powerful tool. It enables manufacturing processes like vapor deposition to occur with an almost perfect purity. In this method, a material is vaporized and then allowed to settle atom by atom onto a surface, creating an ultra-thin, incredibly uniform coating. On Earth, stray gas molecules constantly contaminate this process, but in the hard vacuum of space, the coating forms without a single impurity. This is how we can create the flawless optical films needed for next-generation telescopes or the perfect insulating layers for ultra-powerful computer chips. The logical conclusion of this is the orbiting factory, a facility designed not for assembly but for creation. Companies are already developing plans to manufacture specialty optical fibers in space, fibers that could transmit light with losses so low they would render terrestrial models obsolete. The production of superior semiconductors is another clear goal, with the potential to unlock computing power that would fuel the complex artificial intelligence systems managing these very space colonies. This transforms our entire relationship with the cosmos. Space is no longer a passive destination where we build with what we bring, nor is it merely a quarry for local resources. It becomes an active, high-tech workshop, leveraging its own unique properties to produce the exotic materials that enable its own expansion. This creates a powerful, self-reinforcing cycle, where the products of space manufacturing are used to build more capable factories, which in turn produce even more advanced materials. It is the moment the frontier truly begins to build itself. This entire materials revolution hinges on a silent, digital partner. While we marvel at self-healing polymers and cosmic ceramics, their true power is unlocked by the minds and hands that will build with them, minds made of silicon and hands of precision steel. Artificial intelligence is no longer just a tool, it is a co-designer in the laboratory. The number of possible molecular combinations for a new alloy or composite is practically infinite, a universe of choices too vast for any human team to explore in a lifetime. An AI, however, can navigate this chemical cosmos at lightning speed. It can simulate the performance of millions of virtual material recipes, predicting how they will behave under the blistering radiation of deep space or the abrasive dust of a Martian plane. It identifies the most promising candidates for physical synthesis, bypassing years of trial and error. This is how we move from stumbling upon a great material to intentionally engineering it, compressing a decade of research into a matter of months. But the AI's role does not end on the drawing board. Once a design is finalized, armies of autonomous robots take over. These are not simple remote-controlled machines. They are intelligent systems equipped with advanced vision and a delicate touch. They will be the ones to venture into the airless, hazardous environment of an asteroid mine, using sophisticated sensors to identify and extract the richest ore veins. They will operate the sintering printers that fuse regolith into habitats, working tirelessly through the long lunar night without a single complaint. The true spectacle, however, may be in coordinated construction. Picture a swarm of dozens, even hundreds, of smaller robots descending upon the frame of a new space station module. Like a colony of digital ants, they work in perfect harmony, each unit aware of its neighbors. One group deposits layers of molten metal, another follows behind to smooth and inspect the work, while a third embeds networks of self-healing vascular tubes. An overseeing AI acts as the conductor of this mechanical orchestra, monitoring the entire process in real time. It can detect a microscopic flaw in the printing process and instantly direct a repair bot to the exact location, correcting the error before it becomes a structural weakness. This continuous feedback loop between the digital design, the smart material, and the robotic builder creates a seamless pipeline from idea to object. It is a level of precision and quality control that human hands alone could never achieve in such a punishing environment. This human-machine collaboration is the final, essential ingredient for scaling our ambitions. We can dream of Martian cities, but they will only be built when our intelligent robotic partners are there first, preparing the way, fabricating the foundations, and assembling the structures that will one day become home. The future of space is not just built with smart materials, it is built by smart machines. A permanent presence in space cannot afford the concept of waste. Every gram of material launched from Earth represents an immense investment of energy and cost, making the very idea of discarding anything into the void an unsustainable luxury. This is why the final, and perhaps most profound, leap in our materials revolution is not about creating something new, but about mastering an eternal cycle of renewal. We must transition from a linear take, make, dispose economy to a perfectly closed loop system, where every atom is valued, tracked, and perpetually repurposed. Imagine a future space station equipped not just with manufacturing bays, but with deconstruction docks. A decommissioned satellite, instead of becoming dangerous debris, is gently captured and fed into an advanced reclamation system. Powerful but precise processes, using everything from targeted lasers to chemical baths, break the old hardware down into its pure base elements: aluminum, titanium, silicon, and rare earth metals. These raw materials then become the feedstock for the station's 3D printers, which fabricate a new set of scientific instruments or a structural truss for an expansion. The old becomes new again, right there in orbit, without a single new gram being launched from Earth. This is the foundation of a true circular economy beyond our atmosphere. This principle of renewal extends intimately to the systems that keep us alive. The life support systems of a deep space habitat will be seamlessly woven into its industrial processes. The carbon dioxide we exhale is not merely scrubbed from the air, it becomes a primary resource. Advanced filters and chemical reactors can extract that carbon and feed it into manufacturing systems that build with carbon nanotubes and graphene, turning our breath into the literal backbone of new structures. Similarly, the water recycling systems that purify our wastewater will be designed to reclaim dissolved minerals and compounds, valuable elements that are then diverted to become part of the material production line. What we once considered waste streams are transformed into the most vital of supply chains. This demands a fundamental shift in design philosophy from the drawing board onward. Future spacecraft and habitats will be designed for disassembly from their very first blueprint. Components will be joined with standardized, reversible connections instead of permanent welds. Materials will be chosen not only for their initial performance but for their ease of separation and purity in the recycling stream. A module reaching the end of its life will not be a piece of junk. It will be a carefully organized library of parts and raw materials ready for its next chapter. How do we measure the wealth of a spacefaring civilization? It may not be in the resources it extracts, but in the exquisite efficiency with which it reuses every single atom it has ever brought with it. Establishing these sustainable cycles is the ultimate key to a future that is not only limitless in its scope but infinitely responsible in its practice. This economic transformation begins with a single, staggering figure. The raw materials locked within a single, water-rich asteroid could be valued in the trillions of dollars. We are not talking about science fiction, but a very real future market based on resources that are scarce on Earth yet abundant in the void. Platinum group metals, essential for electronics and catalytic converters, exist in near infinite quantities in the asteroid belt. Water ice frozen in the permanently shadowed craters of the Moon or within carbonaceous asteroids is not just for life support, it is the oil of the new space economy. When split into hydrogen and oxygen, it becomes the very propellant that will power our ships across the solar system. This potential is igniting a modern-day gold rush, but one where the prospectors are autonomous drones and the claims are staked not on land but on orbital trajectories. The first tangible infrastructure to emerge from this rush will be the orbital gas station. Imagine a depot floating at a gravitationally stable point between Earth and the Moon, its tanks filled with propellant harvested from a lunar ice mine. A Mars-bound spacecraft could launch from Earth with mostly empty tanks, a design change that drastically reduces its initial mass and cost. It would then dock at this celestial pit stop, refuel, and continue its journey with a full load. This simple act of creating a supply chain beyond our atmosphere completely rewrites the economics of deep space travel, turning a once impossible voyage into a manageable commute. But the economic engine will not run on fuel alone. The unique perfection of microgravity manufacturing creates products that are simply unattainable on Earth. Perfectly spherical ball bearings with no internal flaws from gravitational sag would allow machinery to operate with near frictionless efficiency for decades. Flawless fiber optic cables drawn in the absolute silence of vacuum could transmit data across continents with virtually no signal loss. These are not mere curiosities, they are high-value commodities that could be exported back to Earth, generating the revenue to fund even more ambitious projects in space. Managing this vast, decentralized off-world economy will require entirely new systems. How do you prove ownership of a resource on an asteroid that is constantly moving, or track the chain of custody for a ton of titanium that is recycled 5 times over in different orbital factories? Emerging technologies like blockchain offer a potential framework for a transparent, tamper-proof ledger, a cosmic deed registry, and bill of lading combined. This fusion of material science and economic innovation creates a powerful feedback loop. Each new material enables a new industry, and the profits from that industry fund the research for the next material leap. The dream of a self-sustaining civilization in space is no longer a question of engineering alone, but of building a viable economy where growth is fueled not by extraction from a single planet, but by the limitless resources of a universe waiting to be used. Yet even the most perfect economic engine requires a set of rules to run smoothly. The moment we begin to harvest water from a lunar crater or mine platinum from an asteroid, we step into a complex legal frontier that is still being mapped. The foundational document for all of this activity is the Outer Space Treaty of 1967. It established the vital principle that space is the province of all mankind, not subject to national claims of sovereignty. But this grand vision was written in an era before private companies could contemplate mining the Moon, leaving a profound ambiguity. If a nation cannot own the moon, can one of its citizens own a piece of a moon rock they have extracted? This legal gray area prompted nations like the United States to pass their own laws, such as the U.S. Commercial Space Launch Competitiveness Act. This act explicitly grants American companies the legal right to possess, own, transport, and sell any space resources they obtain. It is a crucial step that provides the commercial certainty needed to attract massive investment, but it also raises a critical question for the international community. How do we prevent a chaotic scramble for the best celestial real estate and resources? Without a cooperative framework, the same waters that propelled the age of exploration on Earth could lead to conflict in the cosmos. The challenge is to build a system that balances the undeniable need for commercial incentive with the treaty's core ideal of space as a shared human commons. This goes far beyond simple property rights. What building codes will apply to a habitat constructed on Mars? The materials and techniques must be certified as safe by some universally accepted standard to prevent a structural failure that could doom an entire colony. Who will be liable if a piece of a privately owned asteroid mining station accidentally collides with a scientific satellite from another country? And then there is the profound question of planetary protection. We have a responsibility to preserve pristine environments like the subsurface oceans of Europa for scientific study, ensuring we do not contaminate them with Earth-based microbes that could destroy evidence of alien life. Establishing these protocols is not about stifling progress. It is about creating the guardrails that allow it to proceed safely and sustainably. A clear, stable, and fair legal environment is not just a bureaucratic footnote. It is the invisible scaffold upon which the entire edifice of permanent space settlement will be built. Resolving these questions is the final, non-material leap we must make to ensure our expansion into the solar system is a story of peaceful collaboration, not conflict. The strength of a spaceship hull means nothing if the minds inside it begin to fracture under the strain of confinement. After years traveling between planets, the most advanced material in the universe is the human psyche, and it requires an environment crafted with the same precision as a radiation shield. The substances we choose to build with will become the unseen crew members, silently supporting mental resilience. Transparent ceramics do more than just hold back the vacuum. They are digital windows to the soul. An astronaut's daily view of the Earth as a distant blue marble or the sweeping arc of the Milky Way provides a profound cognitive anchor, a constant reminder of the grandeur they are a part of, directly countering the sense of isolation that can grow in a sterile metal box. This connection to the outside is balanced by a deliberate nurturing of life on the inside. Biophilic design, which integrates natural forms and processes, moves from an architectural preference on Earth to a psychological necessity in space. Imagine the walls of a Martian habitat not as cold panels, but as gently curved surfaces grown from mycelium, their organic textures and earthy tones providing a visual and tactile softness that subconsciously soothes the mind. Integrating living plants into these spaces does more than produce oxygen. It introduces the color green, a hue deeply associated with growth and life, which has been shown to lower stress and improve concentration. The habitat itself can become a dynamic partner in well-being. Smart polymers embedded in the walls could allow a crew member to change the color of their personal quarters with a simple voice command, shifting from a cool, energizing blue to a warm, calming amber at the end of a long day. This ability to personalize a small piece of their environment fosters a crucial sense of agency and control in a world otherwise dictated by strict protocols and schedules. Even the soundscape is a material property. Acoustic panels made from foamed metals or grown biomaterials can be engineered to absorb the constant, low hum of life support systems, preventing the auditory fatigue that grinds down nerves over time. Every surface, from the floor to the ceiling, contributes to a sensory experience either of sterile confinement or of a living, responsive home. Getting this material symphony right is not a luxury for a multi-year mission to the outer solar system. It is as critical as the integrity of the airlock. A home that actively cares for its inhabitants is the final, and perhaps most important, material we will ever learn to build. The laboratory where new materials earn their wings is not a place for gentle optimism. It is a brutal, simulated hellscape designed to break them. Before a single gram of self-healing polymer or a sample of bulk metallic glass is trusted with human lives, it must face a gauntlet of trials that replicate the worst the cosmos can offer. Inside colossal thermal vacuum chambers, materials are subjected to a relentless torture. They are baked under searing lamps that mimic the unfiltered fury of the sun, then plunged into a deep freeze that mirrors the absolute cold of shadow, a cycle repeated thousands of times to see if the material will eventually warp, crack, or simply surrender. This simulates the violent temperature swings a satellite might experience every 90 minutes in orbit, for years on end, compressed into a matter of weeks. The assault continues with radiation. Samples are exposed to powerful particle accelerators that bombard them with a concentrated stream of protons and heavy ions, simulating the cumulative, degrading effect of years of cosmic ray exposure. This tells engineers how quickly a material might become brittle or how its color could fade, vital data for anything from a spacesuit's outer layer to a telescope's mirror. Perhaps the most dramatic test is the hypervelocity impact range. Here, microscopic spheres of metal or dust are accelerated to speeds of several kilometers per second, simulating the impact of a micrometeoroid. High-speed cameras capture the moment of collision in exquisite detail, revealing whether a new ceramic composite will shatter or gracefully absorb the incredible energy. Every piece of data from these trials is precious fuel for the artificial intelligence systems that help design the materials in the first place. The AI consumes this real-world performance data, comparing it to its original simulations. When a material fails in an unexpected way, the AI learns, refining its model of molecular interactions and suggesting subtle tweaks to the recipe, perhaps a different ratio of elements or a change in the manufacturing process. This creates a powerful feedback loop, a virtuous cycle where each failure in the test chamber leads to a smarter, more resilient version of the material. This data-driven validation is the bedrock of trust for every space agency and private company. To bring order to this global effort, international standards bodies are working to establish universal certification protocols. The goal is a common language of safety, ensuring that a radiation-resistant alloy certified by one nation's space agency is recognized as equally reliable by all others. This eliminates redundant testing and builds a shared foundation of confidence, which is absolutely essential for the collaborative construction of future stations around the Moon or on Mars. This rigorous, often unseen, process of testing and certification is the final and most critical gatekeeper. It transforms brilliant theoretical concepts into proven, trustworthy building blocks. The silent, empty vacuum of the test chamber is where we build the confidence to finally send our best creations into the boundless void. The ultimate power of the materials revolution may not lie in any single substance, but in the sophisticated combination of multiple advanced materials into hybrid composite systems. Think of a habitat wall not as a single slab, but as a layered defense, a team of specialists working in perfect harmony. Its core could be a lightweight, energy-absorbing foamed metal, providing the primary structure. This is then wrapped in a thick jacket of hydrogen-infused aerogel, a ghostly layer that turns deadly radiation into harmless heat. The outermost skin is a smart polymer, a material that feels the sting of micrometeoroid impacts and instantly begins stitching itself back together. And set within this resilient wall is a viewport of transparent ceramic, a window as clear as glass but with the stopping power of armor plate. Each layer has a dedicated job, and together they create a living environment that is strong, shielded, and self-sustaining. The true engineering challenge and the focus of intense research lies in the handshake between these different substances. The interfaces where one material meets another cannot become weak points. Scientists are developing molecular-level bonding techniques and intricate interlocking geometries to ensure these junctions remain secure, even as the entire structure expands and contracts with the violent temperature swings of space. These composites are not just stacks of ingredients, they are unified systems. A single panel might channel electricity through embedded graphene veins, manage thermal loads with its ceramic matrix, and report its structural health through a network of microscopic sensors. This is the pinnacle of space construction engineering, moving beyond individual material breakthroughs to create integrated, multifunctional building blocks. It is through these sophisticated composites that we will build the resilient and adaptable structures capable of nurturing life for generations, true homes that are far greater than the simple sum of their parts. This deliberate march from a laboratory breakthrough to a trusted part of a spacecraft is a story of patience and precision, a journey that often spans a decade or more. It begins not in a fiery test chamber, but in the quiet hum of a supercomputer. Researchers use advanced simulations to explore a near-infinite landscape of molecular combinations, virtually testing how hypothetical new alloys or polymer chains might behave under cosmic radiation or extreme temperature swings. This digital prospecting identifies a handful of truly promising candidates from millions of possibilities, saving years of blind experimentation. The most promising virtual recipe is then brought to life in a process known as small-scale synthesis. Scientists might create a sample no larger than a coin, a tiny ingot of a novel metallic glass, or a thin square of a self-healing composite. This small piece undergoes its first round of real-world interrogation, with machines measuring its fundamental strength, its thermal conductivity, and its reaction to various stresses. This phase is all about potential, about confirming that the material's core properties align with the grand vision. Any candidate that passes these initial checks then graduates to the prototyping stage. Here, the material is no longer just a sample. It is shaped into a representative component, perhaps a small bracket or a section of a fluid line. This is when it faces the gauntlet. It is sealed inside thermal vacuum chambers, enduring thousands of simulated cycles from blistering heat to deep cold. It is bombarded with radiation in particle accelerators and subjected to brutal mechanical stress tests. The goal here is not just to see if it survives, but to understand exactly how and why it might fail. Engineers meticulously document every microfracture and subtle deformation, gathering the data that will inform the next improved version. This iterative cycle of testing and refinement is the heart of the development process. Perhaps the greatest challenge lies in scaling up. A manufacturing process that works flawlessly to create a coin-sized sample in a university lab often fails completely when trying to produce a sheet large enough for a spacecraft hull. New industrial methods must be invented and perfected to ensure that the 10,000th kilogram of the material possesses the exact same miraculous properties as the first 10-gram sample. Consistency on an industrial scale is the price of admission for a ticket to space. The final, most demanding step is flight qualification. This is no longer about testing a material, but about certifying an entire system. A full-scale component, like a complete fuel tank made from a new composite or a habitation module wall built from regolith bricks, is integrated into a test article that mimics the actual spacecraft. It undergoes vibrations that simulate the violent ride atop a rocket, and it is placed in a chamber that replicates the entire mission profile, from launch to orbital operations. Success here means the material has proven it is not just a fascinating laboratory discovery, but a reliable partner ready for the ultimate responsibility. This long and meticulous journey is the unsung hero of the materials revolution, the essential bridge between a brilliant idea and a foundation for humanity's future among the stars. The sheer scale of this undertaking means no single company or country can build the future alone. We are witnessing the rise of a new industrial model, one forged through global partnerships that blend public vision with private agility. NASA's Commercial Lunar Payload Services Program, known as CLPS, is a perfect example. Instead of building and owning every lunar lander itself, the agency acts as an anchor customer, purchasing delivery services from a variety of private American companies. This creates a competitive marketplace where firms are incentivized to innovate not just their landing systems, but the very materials those systems are made from. A lander leg needs to be both incredibly light for the journey and robust enough to touch down on unpredictable lunar soil, driving the development of new advanced composites and shock-absorbing metallic foams. Across the Atlantic, the European Space Agency operates on a similar principle of collaboration, working closely with industrial giants like Airbus to pioneer new material research for future missions to the Moon and Mars. This is not just about sharing costs, it is about sharing brain power. The most creative solutions often emerge at the intersection of different fields, when a materials scientist from a startup talks to a veteran aerospace engineer from a national agency. Venture capital is now flowing into this new ecosystem, funding a wave of startups whose entire business is in space manufacturing. These nimble companies can take risks and move quickly, developing specialized processes for creating everything from perfect fiber optics to novel medical crystals in microgravity. This global, multi-stakeholder approach creates a powerful synergy. The public sector provides the long-term vision and the initial, stable demand, while private enterprise brings relentless innovation and operational efficiency. Together, they are building an engine for progress that is far more powerful than either could manage on its own, proving that the path to the stars is one we will walk together. This grand vision rests on a foundation of human ingenuity, and that requires a new kind of education. The engineers and scientists who will build with self-healing polymers and program robotic swarms are not just specialists, they are Renaissance thinkers for the space age. Their training must weave together threads from once separate fields, creating a new discipline where a deep understanding of material chemistry meets the principles of orbital robotics and the unexpected complexities of synthetic biology. In response, universities worldwide are launching dedicated programs in space resources and off-world construction. These are not simple add-ons to an engineering degree. They are comprehensive curricula designed from the ground up to equip students with the unique toolkit needed to tackle problems that have never been solved before. They learn how the atomic structure of a ceramic affects its performance under solar radiation, and how to model the economic viability of mining water from a near-Earth asteroid. This foundational knowledge transforms abstract concepts into practical tools, preparing them to become the architects of a new industrial age beyond our atmosphere. But true mastery cannot be found in textbooks alone. The spark of innovation is often lit in the hands-on chaos of a workshop or a laboratory. Student-led projects like building and operating their own cube satellites provide an irreplaceable education. These miniature spacecraft become their classrooms, teaching lessons in systems integration, thermal management, and the harsh reality of orbital physics that no lecture can fully convey. International competitions to design a fully functional Martian habitat push this practical learning even further. Teams must balance structural integrity with life support, radiation shielding with psychological well-being, creating holistic solutions that mirror the complex trade-offs of real-world space missions. This process cultivates a resilient, problem-solving mindset, where failure is not an end but a stepping stone to a better design. To unlock the full potential of our species, this field must cast a wide net. It is essential that these opportunities feel accessible and exciting to a diverse global audience, breaking down the historical and social barriers that have limited participation in the past. When we draw our talent from the entire human population, we gain a vast reservoir of perspectives and creative approaches, which is our greatest asset in solving challenges that belong to all of humanity. The future architects of orbital cities and lunar outposts are sitting in classrooms today, sketching ideas and running simulations. Their education is the most critical infrastructure project we can undertake, an investment in the human capital that will one day transform the limitless potential of space into a lasting home for our civilization. Our newfound power to build among the stars carries a profound weight of responsibility. We stand at a threshold where every technological leap must be paired with a deep ethical consideration of our role in the cosmos. The precautionary principle offers a vital guide, reminding us to proceed with humility and careful study. Before we alter the landscape of a world like Mars with large-scale construction or resource harvesting, we have an obligation to search for any potential native life, however small or simple. Contaminating a pristine ecosystem with earthly microbes, or unknowingly destroying the only other example of life in the universe, would be an irreversible tragedy. This is not about halting progress, but about ensuring our expansion is guided by knowledge and a respect for the unknown. Beyond the question of life lies the challenge of equity. The trillions of dollars in resources within asteroids and on the moon represent a potential fortune that could either uplift all of humanity or create vast new inequalities. Will the benefits of this cosmic wealth be shared broadly, fostering global advancement and lifting communities, or will they be concentrated in the hands of a few powerful nations or corporations, creating a new class division between those on Earth and those who control the heavens? We must also ask ourselves what kind of legacy we wish to leave on these new worlds. Is every crater and valley open for industrial development, or do we designate certain sites as protected wilderness, preserving their pristine beauty for scientific discovery and the wonder of future generations, much like our own national parks? These are not distant philosophical debates. They are urgent, practical questions that need answers before our industrial footprint becomes permanent. Establishing a strong, thoughtful ethical framework now is the essential work that will determine whether our story in space is one of wisdom and collaboration, or one we will come to regret. These visionary structures begin to materialize not as distant dreams, but as logical endpoints of the technologies we are mastering today. The first tangible manifestation may well be the Orbital Hotel, a destination for space tourists seeking an experience beyond any luxury resort on Earth. Its central feature would be a vast dome made not of fragile glass, but of a transparent ceramic, offering a panoramic, uninterrupted view of our planet against the black velvet of space. Guests would float through lounges and suites built from ultralight, self-healing polymer composites, their walls subtly shifting color to mimic a terrestrial sunrise or sunset on demand. This is not a sterile station, but a haven designed with biophilic principles, where living walls of cultivated plants purify the air and provide a tangible connection to the life they have temporarily left behind. Every material choice, from the radiation-shielding aerogel woven into the hull to the foamed metal floor panels that dampen vibration, serves the dual purpose of ensuring absolute safety and crafting a sublime, unforgettable experience. This initial foray into commercial habitation proves the economic model and refines the construction techniques for what comes next. The scale of ambition then expands to address one of humanity's most pressing planetary needs: clean energy. Enormous solar power satellites with wingspans measuring kilometers across could be assembled in high orbit. They would be built not from terrestrial steel, but from aluminum and silicon refined from asteroids, their components programmed to unfold autonomously upon arrival. These silent, graceful structures would capture the constant, unfiltered power of the sun and transmit it wirelessly to receiving stations on Earth as a clean, limitless energy source. The existence of such a system would fundamentally alter our relationship with energy production, turning the space around our planet into a utility that powers our civilization below. Yet the ultimate expression of this revolution is the O'Neill cylinder. This is not merely a large station, it is an artificial world. Imagine two colossal cylinders, each tens of kilometers long and several kilometers in diameter, rotating in opposite directions to create artificial gravity through centrifugal force on their inner surfaces. The framework for such a behemoth could only be built from carbon nanotubes, a material with the necessary strength-to-weight ratio to handle the immense structural loads. The land inside, the very ground upon which millions would live, work, and explore, would be fashioned from the processed rock and metals of asteroids and moons. The interior would be a masterpiece of environmental engineering, with a breathable atmosphere, flowing rivers, and a suspended, artificial sun that cycles through a 24-hour day. This is the culmination of everything we have discussed, from in-situ resource utilization to self-healing materials and programmable matter. It represents a future where humanity is no longer confined to a single planetary surface, but can create and customize its own habitats, tailored for specific climates, cultures, and purposes. The journey from a self-sealing polymer to a cylinder that contains an entire ecosystem is the story of the materials revolution. It demonstrates that our future in space is limited not by physics, but only by the scope of our imagination and our commitment to mastering the atomic building blocks of reality. For every breathtaking vision of orbital cities, there is a grounded and necessary voice of caution. The skeptics are not wrong to highlight the monumental obstacles ahead. The initial energy required to power a lunar regolith smelter is staggering. The risk of creating a chaotic cloud of debris from orbital construction is very real, and the profound biological fragility of the human body in a radiation-drenched, zero-gravity environment remains our single greatest vulnerability. These are not minor details, they are fundamental barriers that demand serious answers. The path forward is not to ignore these challenges, but to dismantle them one piece at a time through deliberate, incremental progress. The first small-scale robotic landers will not build a city, they will perform a crucial proof of concept, demonstrating that we can extract a single breath of oxygen from a handful of moon dust or sinter one small landing pad. Each successful test builds the technical confidence and the political will to fund the next, slightly more ambitious mission. This step-by-step approach transforms an impossible-sounding dream into a series of solvable engineering problems. The threat of space debris is met with a two-pronged strategy of prevention and cleanup. International agreements are already evolving to mandate strict construction protocols, requiring new structures to have designated end-of-life plans. More actively, the same robotic systems designed for assembly can be repurposed for remediation, equipped with nets or harpoons built from resilient bulk metallic glasses to gently capture and deorbit defunct satellites. The most pressing challenge, human health, is addressed with a layered defensive strategy. Advanced shielding materials like hydrogen-rich aerogels form the physical barrier, while ongoing research into pharmaceutical countermeasures aims to help the body itself repair cellular damage from radiation exposure. Mission architecture itself becomes a protective tool, with carefully calculated transit times and the selection of habitat locations that use local mass for natural shielding. Every valid criticism is met not with denial, but with a focused, scientific response. It is precisely by confronting these hurdles with clear-eyed realism that we earn the right to make the revolutionary practical. The ultimate purpose of this entire materials revolution is to answer a single, profound question. How do we ensure that the light of human consciousness never goes out? Every self-healing polymer, every strand of carbon nanotube, is a stitch in a cosmic safety net. We are building an insurance policy for our entire species, a backup of human civilization on other worlds. This is not about escaping a troubled Earth, but about guaranteeing that no single planetary disaster, whether a natural asteroid impact or a self-inflicted crisis, can ever be a final ending. The ability to construct limitless habitats from lunar soil and asteroid metals is what transforms this grand philosophical vision into a practical engineering project. It is the difference between a dream and a blueprint. This higher purpose is what fuels unprecedented international cooperation, as nations recognize that this is a project that transcends borders and unites us in a common human endeavor. The technological breakthroughs born from this effort, from advanced medical imaging to new sustainable building techniques, continually spin off to benefit life on our home planet. The quest to survive among the stars pushes us to achieve greatness, inspiring new generations of engineers, scientists, and dreamers. When we master the atom to build a home on Mars, we are not just solving a technical problem. We are making a declaration about the value of our future. This materials revolution is, at its heart, the tangible expression of humanity's deepest instinct to endure, to explore, and to ensure that our story continues for millennia to come. This materials revolution is fundamentally rewriting the rules of what is possible. We are transforming space from an impassable void into a new domain for human enterprise and expansion, turning a landscape of extreme hardship into a workshop of infinite potential. The toolkit we are assembling is breathtaking in its scope, moving us from hauling every single nail from Earth to fabricating entire habitats from moon dust, from using metals that shatter in the cold to engineering substances that repair their own injuries. This is not merely an improvement in our capabilities, it is a complete paradigm shift. The ancient barriers of cost and durability are crumbling, replaced by a new logic of local resource use and atomic-level design. With in-situ resource utilization, self-healing polymers, and atomically engineered metamaterials, we are making construction in space not just possible, but practically limitless. This grand undertaking, however, requires far more than just new substances. It demands a foundation of international collaboration, where shared goals overcome old divisions. It calls for deep ethical foresight to guide our expansion with wisdom and responsibility. It insists on sustainable, circular economies where every atom is valued and reused. And most importantly, it needs a new generation of innovators, thinkers who are trained to weave together robotics, biology, and material science into a single discipline. The structures that will rise from this effort, from the first permanent lunar outposts to the colossal orbiting megastructures that harvest solar power for Earth, will be more than mere buildings. They will stand as permanent testaments to human ingenuity and our enduring, irrepressible drive to explore and to create. The future is not a destination we passively enter, it is a reality we actively build. With these revolutionary materials in our hands, we are building a future among the stars. The next great chapter of our human story will be written not just on the pages of Earth's history, but across the vast, open volumes of the solar system, and it all begins with the atomic building blocks we are now learning to command.